Hello, here's another batch of thermodynamics questions. We've got part A here. A gas molecule of mass m travelling perpendicular to the wall of a container hits the wall with speed v. Explain why the molecule rebounds with speed v and undergoes a change of momentum of 2mv. Right, so, well, it's going to rebound with speed v because we've got an elastic collision. So that's the first. So we've got elastic collision, which means then if we're coming on with, so we approach with momentum mv, approach momentum equals mv, I don't know what you'd call it, I don't know, depart momentum. Sure, there's a better word to use than that, but that will be minus mv. So the change in the momentum is mv minus mv, which is 2mv. So yes, then so yeah, that's part A sorted. Right, part B. Constant mass of gas occupies a container of constant volume. Use the kinetic theory of gases to explain the increase in the force exerted on the walls of the container by the gas when the temperature is raised. Right, okay, so why does pressure go up when temperature goes up? So we're saying then that and obviously put this in sentences, as temperature goes up, that means that the velocity of the molecules in the gas, the particles in the gas, will go up. So the velocity is going up. That means we're getting more frequent collisions because everything's moving quicker. So we've got more frequent collisions with the walls. And also each collision will also have a greater change in momentum. So with greater change in momentum. So that means then that the force will go up. Because yeah, you're getting, well, force is proportional to the change in momentum, and we've got even more collisions happening. Right, part C. The pressure in the air in the tyres of a car is that at the start of a journey. Oh, and then the temperature goes up. So calculate the new pressure. Right, let's go up here then. So, well, the pressure is proportional to the temperature, and that means we can then do P1 over P2 is equal to T1 over T2, because whatever the constant of proportionality would be, that's going to cancel out when we take the ratios of those things. So we can say that P2, which is what we want, is going to be P1 T2 over T1, which is going to be equal to, what do we have, 2.2 times 10 to the 5 multiplied by 273 plus 54. So what's that, 327. That's our final temperature, divided by, it started at 18 degrees. So that's going to be 291. So we just need to tap all of that in, and we're getting 2.47 times 10 to the 5. So let's say 2.5 times 10 to the 5, missed out the times, pascals. Right, that was that, yeah, assuming that the volume of air stays constant. I don't think I read that bit out, but yeah, it's quite important with this because otherwise this doesn't work. Remember, with all of these gas laws, whatever the thing is, the P, the T, or the V that you're not including, the one that you're not using, that has to be remaining constant. So if that volume wasn't remaining constant, then we can't use that gas law. So that sentence at the end is very, very important. Even though I didn't read it out, I sort of read it, but they always say it, so you sort of get used to it being there all the time. Right, the last part, assuming that the total mass of the car stays constant at that, calculate the change in the total area of the contact of the tyres on the road. Right, okay. So the force that we've got, so we've got pressure is force over area, and we can then work out then what the change in the area would be. The force isn't changing, that's staying at 1200 G, but we can say that our change in area then is going to be the 1200 G divided by the initial pressure, because the pressure's gone up, so we're going to have the lower one first. That's going to be bigger. That's going to be a higher pressure that we've got there. So, I mean, a higher area that we've got there, because the pressure is lower. So we'll need a higher area. the and then we can take off what it will be for the new pressure, which was, let's put the 2.47 in times 10 to the 5, kind of squeezing that in. So that's going to be the change in each one of these. We're working out each one of these is the area for a particular pressure, and then we just subtract the smaller one from the larger one. So that's going to leave us just, well, I'm just going to go straight to the calculator for all of this. It's not particularly interesting. You get 0.005849 thereabouts. That's going to be meters squared. So let's just say 5.8 times 10 to the minus 3 meters squared. Okay, it was quite an interesting bit at the end. There's quite a lot of different concepts have been brought into all of this. So that last part is a trickier calculation than they often have on these questions. All right, let's see what we got up next. State in words Boyle's law. Right, so we can't just write down pressure is inversely proportional to volume. You're going to have to write this out. So you're going to want to say that the pressure is inversely proportional to the volume, and you need to say for a fixed mass of gas at constant temperature. Mass of gas at constant temperature. So again, turn that into a proper sentence, particularly this bit here. So actually write out pressure is inversely proportional to volume rather than writing it out like that. So that's that. Then we've got figure 6.1 is a graph showing the relationship between the quantities involved in Boyle's law. Label the axes appropriately. You can put them either way around. So let's do pressure and 1 over volume there. You could do 1 over volume and pressure. It doesn't matter which way around you're doing them because they're still going to be proportional to each other. So that is fine. A gas cylinder of internal volume of that contains compressed air at 21 degrees C and that pressure. There's the molar mass. So work out the number of moles of air in the cylinder. Right, so PV equals nRT. We want to go for that one because that is our number of moles. So N is going to be equal to, our pressure is 1.2 times 10 to the 7. Our volume is 0.05. R is 8.31. And our temperature is, 21 degrees, so 294. So that gives us 245.6, so let's say 250 moles. 250 moles, that's that bit. The mass of air in the cylinder, so they've given us kilograms for mold air, so we just need to multiply by 0.029, which is giving 7.12, so 7.1 kilograms. Right, that was a couple of easy ones to work out. Then an additional 1.5 meter cubed of air at 21 degrees C, atmospheric pressure of that is pumped into the cylinder. Calculate the new pressure. Right, so we need to get how many moles have been added to all of this. So we can do this again and say, well, the new number of moles is going to be 1 times 10 to the 5 multiplied by 1.5 divided by 8.31, and that's the same temperature, so 294. That gives us another 61.4 moles. Now we need to put that into a new PV equals nRT. So P is going to be equal to what we're doing. We've got the total number of moles now is 245 plus 61. Well, that'd be 246 plus 61, say 307 moles, multiplied by 8.31, multiplied by 294, divided by, 0.05. That's coming out at, it's a lot to type in, 1.5 give or take times 10 to the 7 pascals, which makes sense. You started at 1.2 times 10 to the 7. We've shoved some more air in, so the pressure's gone up a bit. So there we go. That's another question done. Right, now what have we got? So part A here, define specific heat capacity. Now they haven't said do it in words, so you can go either way here. You could say that it is the energy required to raise the temperature of a unit mass of a substance by a unit temperature. So you could write that out in a sentence, or because they haven't said you've got to do it in words, you could do the C is equal to E over M delta T, and then say what all of these things are. Then just define, it's probably the easier way of doing it. So you can say, C is the specific heat capacity. I'm going to write all these out. E is the energy supplied to a particular substance. M is the mass of the substance, and delta T is the temperature change. So that's probably an easier way of doing it. Describe the difference between the latent heat of fusion and the latent heat of vaporization. Right, so writing these out, you'd want to say latent heat of fusion is the energy required to change a substance from solid to liquid, and then the latent heat of vaporization is the same thing, but you're changing the substance from a liquid to a gas. So it's that solid to liquid versus liquid to gas. So pretty standard definitions on all of those. Right, part B, the graph in figure 4.1 shows the variation of temperature with time for a fixed mass of substance when heated by a constant power source. Right, so we've got constant power, we've got fixed mass. A, it's solid, E, it's a vapor. Right, okay. So and then we're going to have the liquid in the middle here. So we've got solid there, liquid there, and then we've got a vapor at the end, and we've got our latent heats in between. Describe the changes taking place in the kinetic energy and potential energy of the molecules for the following sections. Right, so from A to B, we got a temperature change. So we're getting that the kinetic energy must be going up, and the potential energy is always going to be increasing through here anyway. So we're getting kinetic energy up, potential energy up for A to B. And although most of it's going to be going into the kinetic, so it's mostly kinetic, so you might want to put that in there, but we are getting some potential energy changes. Then we're going to have from B to C, there's no temperature change, so the kinetic energy is going to stay the same, and it's all going into potential energy. So that's what's happening there. Again, just putting those into sentences. Then we've got what we got. State and explain what you can conclude from figure 4.1 about the specific heat capacity of the substance in solid state compared with liquid state. Okay, so we've got a gradient here so let's go up here. So the gradient is the temperature divided by the time, and the time, so the energy, because we've got this constant power source, the energy is proportional to the time. So really we've got here is the temperature divided by the energy. So let's go to our E is mc delta T. So if we've got temperature over energy, then we've got 1 over mc. So the gradient is going to be, well, let's leave it up here, proportional to 1 over the specific heat capacity. So if we've got a higher gradient, we've got a lower specific heat capacity. So that means that C for the solid is going to be less than C for the liquid, because it's got a higher gradient. So yeah, it's just unpicking all of that stuff. Yeah, so that's brought us to the end of that. I thought they were going to ask us more about maybe what's going on with these latent heats, but that doesn't seem to have come up. Right, let's squeeze in another. Oh, we're still on the same question again, right? It's another one that's moved on to the next page. The electric heating element of a bathroom shower has a power rating of 5 kilowatts. So we're trying to test the accuracy of that by doing a rate of flow thing. They've given us a whole load of data here. So we've got to show that the power heating, yeah, so we're checking that it is actually showing that. So what have they given us here for information? We've got a start and end temperature. So that change in temperature here is, what's that, 19.3 degrees C. Well, we can actually put that as Kelvin. So, because we're going to be wanting to work in Kelvin. We've got a rate of flow of water in cubic meters per minute and then a density of water. So we're going to want to combine those to get a a mass per second is going to be more useful on this. So that will be, we got 3.6 times 10 to the minus 3 is our volume per minute. So if we divide that by 60, then that's going to be our volume per second. Multiply that by our density, and that is going to be our mass per second. So that's not going to be a lot. That's going to cancel with that. So we're going to get, oh, we are going to get something small. It's 0.06 kilograms per second is what we're getting there. That's our specific heat capacity. So the energy per second is going to be our mass per second multiplied by the temperature change multiplied by the specific heat capacity, which is coming out, and you can check all that from the units. We're just making all these units cancel out. That comes out of 4864. So that's as good as 5 kilowatts. So yeah, that's all good. That's what they want us to show. State and explain a possible source of uncertainty that might affect the reliability of the test. Right, so what can go wrong with these bits of data we've got here? Not so much these bottom ones. The density of the water isn't going to change that much, I wouldn't have thought, or the specific heat capacity. I suppose the density, you might have different, yeah, no, well, I mean, that is what the density of water is. It's going to be that the flow rate might change. We might get different water pressure. So let's go with that. So we could say changes in the water flow rate due to changes in water pressure, due to changes in water pressure. So we could have that as one thing. We've certainly got the temperature of supply could change as well, because sometimes you get this, that you get a big sort of glug of cold water turns up from a, you know, some distant reservoir or something like that. So we could have a change in water supply temperature. That happens quite a lot. So you can notice this sometimes when you get into you know, maybe in the spring or something like that, where they'll release a big load of water from, we sometimes get it, a water turn up from a reservoir halfway up a mountain in Wales, and then it suddenly hits us, and it's like, wow, okay, right, the boiler's having to work overtime in order to heat all of this up. So you can get change in water supply temperature. So maybe either one of those will do. Right, that is definitely the end of that question. So I'll leave this video here as that's gone through 3 more questions.